Welcome back, everyone. In this video, I'll be going over the lecture for the definite integral. Now, what we're going to do in this section is, and I know some people may have taken calculus before, they know what an integral is. We're not going to be dealing with what you saw before. All an integral, a definite integral, is going to be representing. It's going to be a way to represent area under the curve. So pretty much the main point of this section is to understand that we don't want to say area under the curve of some function on the closed interval a to b every time. We want a much shorter way to write this. And the way to write this is actually by something called a definite integral. Now, exactly what I have highlighted here, area under the curve of some function on the closed interval a to b, this is what this represents. So I'm going to go through and just explain the parts here. This long S shape here is actually called the integral sign. The A and B, they are the bounds on the interval. So where you're finding the area, A is the lower one, and B is the upper one. Now, in general, when we deal with actual numbers here, we'll want A to be the smaller one and B to be the bigger one. But it is possible that you're given a problem in the future where A is actually the bigger number, or the number on the bottom is actually the bigger number. So when we refer to lower bound and upper bound, we're very literally referring to the bottom and the top on the integral. In general, these are just called the bounds. So A and B are called the bounds. Some people actually also call them limits of integration. So they tell you what range from A to B, what actual numbers you want to find the area under the curve. The f of x is the area, the function we're actually finding the area under the curve of. So this is the function to find area under the curve. Okay, so if we have like x squared there, we have a parabola. That means we're finding some area under the parabola. And then the dx here, so this is the easiest thing to forget because it doesn't seem like it does much. But dx is a couple things. So it is important to remember. Just very quickly, I'll remind you that in general, when we talked about the Riemann sums, how we got the exact area, you don't need to write this down, I'm just reminding you. We had that formula like b minus a over n times f of I over n times b minus a. And then if a wasn't 0, we had to add an a. Well, what's happening here is when you actually go through and convert this, this is just notation, but it all means something from this original. So notice that I left off the rest, but all I'm really pointing out here is that this b minus a over n, this was the width of our rectangles. So if we were going from a to b and we cut it up into n rectangles, then the width of each rectangle was b minus a over n. That's exactly what dx means. It means it's representing the base of the rectangle, but in general, it's just two letters dx. So in general, what this really does is it tells you the variable that you are finding the area under the curve with respect to. And that might seem like it's not really that important, but when we talked about doing derivatives, we saw plenty of examples, whether it was implicit differentiation or just examples where we had like a k times x. We had to know that we were doing d over dx. So this dx is a very similar idea in that it not only is important because it means something. So the d over dx meant do the derivative with respect to x. This dx is representing part of the area that we're finding. But in general, if you don't write the dx and you have multiple letters in your formula, like x and y, x and t, a and b, whatever they happen to be, you don't know which letter you're quote unquote integrating with respect to. So it's very important. And a big topic in integrals is actually not only dealing with just x, but doing something that causes you to change the letters as you go. So it's very important to write in. It's so important that if you do not include the dx, you will absolutely be doing it incorrectly. Even if you do all the math steps right, if your dx is not there, then you're not really doing it properly. It's sort of like when you don't write the d over dx, when you don't write the limit, when you're doing a limit. You need to make sure it's there. All right. Now, just to specify and relate it back to last section is that when f of x is greater than 0, so when it's above the x-axis on your interval a to b, the definite integral matches exactly what we were talking about in last section, the area under the curve. Well, going forward, we don't want to do just functions that are positive. We have plenty of functions that are negative. And if your function is negative at some points, then the definite integral gives you the area of that shape, but a negative of that area. Because in general, when we say area, we would never say the area of something is negative. But if your curve is under the x-axis, then when we do the integral of it, the definite integral of it, it will be negative. So to put this into an actual example with numbers, I'm going to have, let's say a is 1 and b is 4, and the function, I'm going to use a very easy example because I want to be able to compute the area very easily. Let's say -2, and we have the function y equals -2, or f of x equals -2. Well, if we want to compute the definite integral from 1 to 4 of f of x dx. Now I'm not going to plug in what actually x is. What f of x is. It's equal to -2. This is just to illustrate what we're doing. Well, we know we're finding the area under the curve, but because the curve is below the x-axis, we want to actually visualize the area when we draw the line up to the x-axis, and we want this area. So this area is pretty much exactly this definite integral. However, because we are below the x-axis, it is negative. So when you figure out this area, all you do is you figure out the area of the rectangle itself. Now this has length 3 and height 2, so the area is 6. And because of the negative sign here, what is happening is you actually have -6. So the point here is that the area of A equals 6, but the integral from 1 to 4 of f of x dx equals -6. So that's just something you have to look out for. If you want to actually prove it, it's pretty tedious because you have to go through and actually compute the sum. Way back when we did in last section, mess around with negative signs. But basically what happens is when you have a negative sign, you just get a negative sign everywhere and it gets factored out. Okay, all right, so we're not going to talk more about negative area besides just the idea. So when we see stuff below the x-axis, remember that the real area is positive, the definite integral, what we're focused on now is negative. All right, and that's pretty much what I have outlined in that little section. Now, in general, when you do a definite integral, you have to break it up into pieces where the function is below and above the x-axis, since you can go above and below with a function. And this next example I have set up for you is really to illustrate this point. So this says the graph of h below consists of 2 straight lines and a semicircle. So you definitely need to be told specifically what shape it is, because that's going to pretty much all we know about doing integrals at this point is that we can calculate it by doing their area. So this straight line will make this a shape. This is a semicircle, so this shape is going to be a semicircle, and this straight line makes this area a triangle. What we're going to do is we're going to evaluate each of those 3 parts as a definite integral, and then using the idea of what area is, we can actually do the entire integral all at once. All right, so this function is only defined from 0 to 7. We can't see anything else, which means when we're doing this last one, We're actually finding the area under the whole thing. Well, before we get there, let's go ahead and do one at a time. So our first shape, I'll call this A1, is right here. And because it's positive, so this area is above the x-axis, this is when we do the definite integral from 0 to 2 of h of x, we get just the area of that shape, which is a triangle. Now the area of a triangle is 1/2 times base times height. A right triangle, but it is a right triangle. We got a right angle there. So we got 1/2. The length of the base, we're going from x is 0 to 2, so that is 2. And the length of the height, we're going from x is 0 to x is 4, so that is 4. And we get, well, the 1/2 and 2 make 1 times 4 is 4. So when we're asked just to integrate from 0 to 2 of this h of x dx, we get 4. Right. Now the next little section here is from 2 to 6. You'll notice that it's perfectly marked off in each shape. So as soon as we hit 2, and when we go from 2 to 6, we get this next shape. That is a semicircle or a half of a circle. So this is like our A2 here. And when we integrate from 2 to 6, this is pretty much the area of the semicircle. Well, what do we have to make sure we do? Because it's below the x-axis, we need a negative. Right, so whenever we do an area, it's always positive, but because our graph is below the x-axis here, it's going to be negative. Well, the area of a circle is pi r squared. So we have pi. What is the radius here? If you're not sure, keep in mind that the diameter would be from here to here, from 2 to 6. So the radius r is half that. And if the whole length from 2 to 6 is 4, then the radius being half that is 2. So we got pi times 2 squared. You do have to be careful though, this is not a whole circle. This is the area of an entire circle. The area of half of a circle, we would take its area and multiply by 1/2. Okay, so pi r squared is the area of a circle, and because we only have half of it, we multiply by 1/2. Now you simplify this, leave the pi, don't write a decimal. We got 2 squared is 4, times 1/2 is 2. So this is -2 pi. And now the last little bit from 6 to 7, that's this little section here. This is like our A3, if we want to give it a name, but it's another triangle. And it's also above the x-axis again. So this is the area of the triangle. It's above the x-axis, so we don't have to worry about a negative sign. We have 1/2 times base times the height. Now the base is length 1 because that goes from 6 to 7. What is the height? The height, well, it starts at 0 on the top. It goes to the y value here. I drew it over here, but just in case you couldn't tell, I also gave you the coordinates of this point. The height is 1. So this is also times 1. And we get 1/2. Right? So that is the individual. Each little segment has that area. Now, what is the entire area? If we add these three areas together, well, because it's a definite integral, we can't just add the areas together. We have to add the integrals together. So this is positive, this is negative, this is positive. But we already have all the numbers here, 4, -2 pi, and 1/2. So our final answer from x is 0 to 7, so that's why we're going the entire way. We have 4 plus, and then -2 pi, plus, and then 1/2. So we're just adding all of these numbers together. Now you're not going to be able to simplify too much. You can simplify the 4 plus 1/2 because there's no pi with it. You multiply it by 2 over 2, then you get 8 over 2 plus 1 over 2 is 9 over 2. And then the plus -2 pi, well, that's just minus 2 pi. And that would be this quote unquote area. It is the definite integral from 0 to 7. So when you have many pieces like this and you want to find the definite integral, you have to break it up in parts. Where is it above? Where is it below? The stuff above gets a positive, the stuff below gets a negative, and then add them all together at the end. Right? And as you do more of these on your own, you'll start to do these a little bit quicker. But really the purposes of thinking about these as area and having the picture pre-drawn for us is just to know how to go through this. In general, we'll have a formula. We won't have a picture. And in this section, when we deal with the formulas, we're going to have to graph it to figure it out. Now, I think this is a good place to stop because the next little section is the properties of definite integrals, and they are very important, and I don't want it to drag on at the end of a video. So I will see you in the next video.